Hello and welcome. Today we're going to explore the profound transformation happening at the intersection of material science and artificial intelligence. Specifically, we'll be taking a deep dive into how AI is reshaping the entire world of advanced polymer manufacturing. The way we create and work with polymers is undergoing a fundamental structural change. For a long time, the field operated on an empirical paradigm, often called the Edisonian approach of trial and error. But we are now moving rapidly toward a data-driven framework, a field known as polymer informatics. This shift is driven by necessity. Polymeric materials are inherently complex. They're defined by a stochastic and hierarchical architecture that spans from the molecular level, the nanostructure and self-assembly, all the way up to the processing and macroscopic bulk properties of the final product. As demand accelerates for high-performance, sustainable, and functional polymers in critical sectors like aerospace, automotive, energy storage, and biomedical engineering, the traditional slow development cycle has become an unsustainable bottleneck. This is where artificial intelligence and machine learning come in. When integrated with automated hardware and the Internet of Things, AI provides the primary mechanism to dramatically shorten these timelines, facilitating the rapid discovery of new chemistries and the optimization of advanced manufacturing processes. At its core, machine learning, or ML, uses algorithm development and data training to enable computers to adaptively learn from data. They can then perform complex simulations and make decisions, all while optimizing a given process. Broadly, we can categorize machine learning into a few key areas. First, there's supervised learning, where the data used for training is labeled. Then we have unsupervised learning, which works with unlabeled data. Beyond these, reinforcement learning focuses on decision-making through environmental feedback. An agent learns by receiving rewards or penalties for its actions. And a powerful subfield within all of this is deep learning, which utilizes complex architectures called deep neural networks to perform both supervised and unsupervised tasks with very high levels of abstraction. Let's visualize how these concepts have evolved and how they apply to polymer science. The journey begins in the 1950s with traditional mathematical and statistical models. By the 1980s, machine learning emerges, branching into supervised, unsupervised, and reinforcement learning. Then, around the 2010s, deep learning and its various neural network architectures like convolutional and recurrent neural networks become prominent. Now, let's connect these to practical polymer applications. In supervised learning, we have two main tasks. The first is classification. For example, we could train a model to predict whether a given polymer is biodegradable or non-biodegradable based on its features. The second task is regression, where we predict a continuous value. An example here would be predicting the mechanical strength of a polymer. In unsupervised learning, the goal is to find hidden patterns in data. One technique is clustering, which could be used to identify novel families of polymers within a large dataset. Another is dimensionality reduction, which helps us take a complex polymer property dataset and simplify it for easier visualization and analysis. Reinforcement learning is particularly exciting for automation. Imagine an AI agent in a lab environment. It can optimize polymer synthesis by testing different conditions. Based on the reward, say a higher yield, it learns and refines its strategy, eventually discovering the optimal parameters for a polymerization reaction on its own. And underpinning many of these advanced applications is deep learning. It excels at processing complex, high-dimensional data. We can feed it input from sophisticated analytical tools like atomic force microscopy, transmission electron microscopy, or nuclear magnetic resonance spectroscopy. The deep neural network, with its input layer, hidden layers, and output layer, can then learn to perform tasks like generating new polymer structures, predicting a critical property like the glass transition temperature, or classifying a polymer solubility. The foundation of this AI-driven approach is the field of polymer informatics, an interdisciplinary domain that uses data science to establish quantitative relationships between a polymer's chemical structure and its macroscopic performance. However, polymers present a unique challenge compared to small molecules. A small molecule can be easily represented by a standard chemical descriptor, but a polymer's properties are defined by distributions of chain lengths, or dispersity, as well as complex branching patterns and stereochemistry. Developing machine-readable descriptors that can accurately capture this stochastic nature is a critical and ongoing area of research. To tackle this, researchers are now applying multitasking deep neural networks. These powerful models can predict multiple properties simultaneously. For instance, the glass transition temperature, tensile strength, and gas permeability, by learning shared representations from large datasets. But this leads to one of the most significant hurdles in the field: data scarcity. Polymer research and manufacturing often operate with limited and not yet well-curated datasets. One promising strategy to mitigate this is transfer learning. This involves taking a model that has been trained on a large general materials dataset and then fine-tuning it on a much smaller specialized dataset. This approach often leads to improved accuracy for specific applications without requiring massive amounts of new data. Another crucial evolution is the shift away from so-called black box models towards what is known as physics and chemistry-aware machine learning. By integrating fundamental physical laws and chemical theories directly into the machine learning architecture, researchers can ensure that the AI's predictions remain within the boundaries of scientific reality. This is particularly important for predicting complex behaviors, like the degradation pathways in biodegradable materials or the multi-property trade-offs in energy storage materials. Integrating domain knowledge like the Flory-Huggins solution theory or insights from molecular dynamic simulations allow these algorithms to generalize better and make more accurate predictions, even when working with smaller datasets. To better understand the tools at our disposal, let's briefly compare some common AI algorithms. For regression tasks, predicting a numerical value, we have models like linear, lasso, and ridge regression, as well as artificial neural networks. Their advantages are that they are relatively easy to implement and can handle high-dimensional data. However, they can suffer from overfitting and may rely on assumptions of linearity. We evaluate them using metrics like R-squared, mean squared error, or root mean squared error. For classification tasks, assigning a category, we use algorithms like k-nearest neighbors, support vector machines, and random forest. These are excellent at handling imbalanced data and outliers, are scalable, and can make fast predictions. Their downsides include sensitivity to noise and being more of a black box, making them harder to interpret. We measure their performance with metrics like accuracy, precision, recall, and F1 score. For clustering, grouping similar data points, we have methods like k-means and dbscan. They are fast and robust to outliers, but they often require the number of clusters to be predefined and can perform poorly in high dimensions. Their success is typically measured with internal metrics like the silhouette score. Finally, deep learning models like ANNs, CNNs, and RNNs offer very high accuracy and are excellent at automatic feature detection and modeling sequential data. However, they require large amounts of data and significant computational power, can suffer from issues like vanishing gradients, and are notoriously difficult to explain. Now, let's see how these tools are being applied in one of the most dynamic areas of polymer manufacturing, additive manufacturing, or as it's more commonly known, 3D printing. Additive manufacturing is an essential tool for innovation. It allows for the rapid, cost-effective fabrication of complex objects, making it ideal for the discovery of new polymer materials. We can even create so-called 4D printed objects, which use stimuli-responsive materials that can change shape or function in response to an external field. To achieve superior properties, especially a high strength-to-weight ratio, we often turn to composites. But whether we're working with thermoplastics, thermosets, or elastomers, optimizing the material and the printing process is a complex challenge. Statistics are foundational to this optimization, which is precisely why machine learning methods are so powerful here. Artificial intelligence and machine learning are now being applied across all aspects of this field to innovate designs and enhance efficiency. Using AI/ML workflows, we can optimize the materials themselves, the 3D printing methods, and the characterization techniques. We can even augment this process with large language models and advanced simulations. The ultimate goal is to achieve faster and better relationships between a material's structure, composition, processing, and its final properties, ideally removing the human in the loop for routine tasks. Let's visualize this workflow. At the top, we have machine learning, which encompasses paradigms like supervised, reinforcement, and unsupervised learning. These paradigms use various models and techniques, like decision trees, neural networks, or clustering algorithms, to perform specific tasks, such as regression or classification. These tasks, in turn, enable critical industry applications in manufacturing, including predictive maintenance, quality control, process optimization, and industrial automation. Now, consider a specific example. Imagine we want to predict the dimensional accuracy of a 3D printed cylinder. We can build an artificial neural network. The inputs to this network would be the printing parameters, things like slice thickness, the raster-to-raster air gap, the deposition angle, the bead width, and the number of shells. These inputs are fed through the hidden layers of the network, which learns the complex nonlinear relationships between them. The output is the prediction, the percentage difference in the final length and diameter of the printed part compared to the design. This allows for precise control and optimization before a part is even printed. The potential for AI in 3D printing is vast. Based on available databases, AI can effectively optimize material synthesis and the printing process itself, automating the path to informed decision-making. The key benefits include, first, the discovery of new high-performance materials. Second, enhanced optimization of recipes and processes. Third, more efficient quality control. And fourth, automated design and functionality development. A critical area here is real-time defect detection. By developing methods to spot defects as they happen, we can create a feedback loop to correct the process on the fly. In situ monitoring allows us to link process parameters, like the characteristics of the melt pool, directly to final material properties like porosity and mechanical strength. This vision of a fully automated, intelligent laboratory is known as the self-driving laboratory, or SDL. In an SDL, the manual operations of synthesizing, characterizing, and analyzing data are all automated. The decision-making, what experiment to run next, is handled by machine learning-driven algorithms that intelligently explore the parameter space. The role of the human expert here is not obsolete. In fact, it becomes even more critical. The scientist's job is to define the scientific questions, constrain the search space, select the appropriate reaction protocols, and provide oversight. Consider a continuous flow reactor for synthesis. In an SDL setup, reaction parameters like temperature, residence time, and reagent amounts are precisely controlled. Reagents can be autonomously selected using robotic liquid handlers or switch valves. The output of the reactor is fed directly into an online analytical module, perhaps an HPLC, an infrared spectrometer, or an NMR, which measures the outcome, such as the reaction yield. This data is then fed back to the AI agent, which uses it to select the conditions for the very next experiment in a continuous, optimized feedback loop. One of the core challenges in developing these SDLs is creating the software and interfaces that allow for seamless information exchange between the machines, the AI, and the human user. The impact of AI, however, extends far beyond the research lab and into the heart of industrial production. Primary manufacturing processes like injection molding, extrusion, and polymerization are being revolutionized by real-time monitoring, predictive maintenance, and closed-loop process control. In plastic injection molding, AI is transforming statistical process control into a fully automated 100% inspection system. By embedding pressure and temperature sensors directly within the mold cavities, AI models can calculate critical product characteristics like dimensions and weight for every single part produced, all in real time. This allows for dynamic defect correction during the molding process itself, minimizing material waste and energy consumption by optimizing injection speed, pressure, and cooling time for each specific cycle. A schematic of such a system shows the process. As the plastic is injected into the mold, in-mold pressure sensors and system pressure sensors collect data. This analog data is sent to an amplifier and a data acquisition module, which digitizes it and sends it to a computer. On the computer, a multi-layer perceptron neural network, a type of deep learning model, processes this real-time data and predicts the quality of the part being formed. Let's compare this AI-driven approach to traditional quality control. Traditionally, inspection is done through random sampling using statistical process control. With AI, we get automated inspection of every single part. The data source for traditional methods is post-production measurements. For AI, it's real-time cavity pressure and temperature sensors. Defect detection in the old way is manual or optical, and it happens after the fact. With AI, we get a prediction of characteristics like weight and dimensions mid-cycle, before the part is even finished. Traceability is traditionally only at the batch level. AI provides full, individual part-level documentation. And most importantly, waste reduction. The traditional approach is reactive. You reject a batch of faulty parts after they've been made. The AI-driven approach is proactive. It allows for parameter adjustments on the fly to prevent defects from occurring in the first place. A similar transformation is happening in polymer extrusion. This process is highly sensitive to fluctuations in temperature, pressure, and mixing speed. IoT-enabled sensors now provide real-time data streams that AI algorithms can analyze to adjust these parameters dynamically. For instance, a real-time surface defect monitoring system can be integrated directly into the production line. As the extruded polymer tube emerges from the extruder and passes through a cooler, it enters a monitoring system equipped with cameras. These cameras feed a live view to a notification screen, where an AI can instantly flag any surface defects, allowing for immediate correction. AI is also making inroads in more specialized areas of polymer manufacturing. Consider systems involving biomolecules and small organic molecules, which are critical for applications in energy and medicine, like drug delivery. The properties of these complex systems are often highly dependent on weak forces and chemical bonding that occur during crystallization or self-assembly. Predicting properties here is incredibly challenging due to the large processing parameter spaces. Now, using inverse engineering and physics-informed machine learning, it's possible to make accurate predictions even with a small dataset. In drug delivery, for example, AI algorithms are being used to predict therapeutic outcomes, optimize patient-specific formulations, and even connect with real-time biosensors to drive automated drug delivery. On the other end of the spectrum is the manufacturing of high-performance polymer composites, which poses complex engineering challenges. A key technology here, especially in aerospace, is automated fiber placement, or AFP. This involves a robotic arm laying down multiple strips of carbon fiber prepreg onto a surface to build large, complex structures, like fuselage sections. The quality of the final part is dictated by precise control over parameters like temperature and layup speed. Any inconsistency can lead to defects that can reduce the structural integrity of a component by as much as 30%. Historically, identifying these defects required manual visual inspection, a major bottleneck. Now, AI is being integrated directly into the AFP process. Machine learning and deep learning algorithms can analyze sensor data in real time to identify irregularities or flaws with over 95% accuracy. Furthermore, AI-based process planners can learn from historical data and simulations to handle complex contoured structures, generating optimized fiber placement paths that minimize defects and maximize structural performance, much like a highly experienced human planner would. The improvements are dramatic. Compared to manual AFP, AI-optimized AFP can increase the layup rate from the limits of human speed to up to 50 meters per minute. Inspection time, which could take up over 60% of total production time, is significantly reduced through in-situ AI monitoring. This leads to productivity gains of up to 450%. Material waste can be slashed from as high as 62% down to around 6% through precise placement, and overall manufacturing costs can be reduced by up to 43%. Beyond performance, AI is a critical tool for advancing polymer sustainability. One application is in AI-driven bioplastic screening. In one study, an informatics workflow was used to find alternatives to petroleum-based plastics for food packaging. It predicted 8 key properties across a massive library of 7.4 million potential polymers, filtering them to identify candidates that not only had the desired properties, but also exhibited high chemical recyclability. The other side of sustainability is dealing with existing plastic waste. Chemical recycling, which breaks down plastics into their molecular building blocks, is a complex process that benefits significantly from AI-driven optimization. AI helps in several key ways. First, it can optimize catalysis, for example, by helping to design more efficient enzyme catalysts for breaking down polymers like PET. Second, it can predict reaction kinetics. Neural networks have been trained to predict PET hydrolysis conversion efficiency with high accuracy. And third, AI can model pyrolysis oil yields. Models can predict the oil yields from real-world mixed plastic waste streams, allowing recycling facilities to prioritize the most promising feedstocks for chemical upcycling. Let's look at an example of how AI can be used in polyester design. Polyesters are composed of diacid and glycol monomers. These can form linear chains, branch chains with the addition of a third monomer type, or even cyclic chains. A database of such materials shows a wide, heterogeneous distribution of properties like glass transition temperature and intrinsic viscosity. An AI model can take as its input the composition, the specific acid and glycol monomers and their percentages, along with initial resin properties. It can then predict the final properties of the resulting polymer. This allows researchers to perform an inverse design. They can specify the target properties they want, and the AI can suggest the monomer composition needed to achieve them. With all this potential, it's also important to discuss the barriers and future directions. The shift to AI-driven manufacturing is changing the very nature of work. The modern operator is becoming a co-pilot, working alongside AI systems and using smart dashboards that don't just show what to do, but also explain why. This reduces fatigue and allows the workforce to focus on higher-level tasks, like continuous improvement, compliance, and safety. However, several critical barriers hinder universal adoption. The community is still heavily anchored in the traditional research paradigm, and moving to a fully data-driven model requires overcoming both technical and cultural obstacles. The grand technical challenge is the lack of high-quality, diverse, and well-tagged datasets. To address this, the industry is moving toward fair data standards, meaning data should be findable, accessible, interoperable, and reusable. This will ensure that experimental results can be shared and utilized by machine learning models globally. Finally, there is an increasing focus on explainable AI, or XAI. We need models that don't just find an optimal material, but also provide insight into the underlying mechanisms that make it optimal. This is essential for gaining the trust of engineers in high-stakes industries, like aerospace and medical devices, where an unexplained prediction can lead to unacceptable risks. The trajectory of AI in the chemical and materials science market points toward a historical expansion. The future of polymer manufacturing will be defined by the seamless fusion of digital twins and physical domains. As research continues to bridge the gap between algorithm benchmarks and industrial applications, a circular economy, driven by machine learning automated designs and materials, will likely become a technical reality through the sustained integration of artificial intelligence and advanced polymer manufacturing.